Hi, welcome to class. Today we're going to be talking about something really important, and that is the whole design process. And we're going to get started by looking at a specific design that we can use the stuff we've learned already in the course, such as the combinational logic that we've learned about. So we're going to apply that to an actual real design and demonstrate its functionality. So first off, I want to start off with talking a little bit about what this real world example does. We'll start by looking at a description of the problem. So we're going to be doing something that relates to changing the way a 7-segment display shows numbers. And this is something that has application in lots of industries. One application in particular could be the automobile. Lots of companies have in the past experimented with this thing called a heads-up display. So the heads-up display basically shines the number, like the speed limit, the speed the vehicle is traveling, up on the windshield. So they'll reflect it off the inner part of the windshield, generally in the evenings, when it's dark, but they also can do it in the day if they have a special material that's highly reflective to the light, so that when the person's looking out at the road, they'll see the digits for the speed hovering kind of in the air next to them. And to do this, the LEDs that are used to project this number tend to be in the dash. And so the reflection causes the light to bounce off the inner part of the window, and then the person can see it. Because of that, you need to project a mirror image of the number from the display onto the window, so that when it gets to the person's eyes, it looks right side up. And this is kind of tailored to that idea, except in this case we're going to be doing it sideways because it's a little easier to explain that way. So let's take a look at what it does. And so from the standpoint of what we're doing, we're going to basically start off with a value switch. And the value switch inputs any value between 0 and 15. So it's a 4-bit value. And that value is going to be fed into our FPGA. And then the FPGA is going to display the digit or the number onto the 7-segment display. This is just your standard 7-segment display. We can control whether or not it displays the actual number or a mirrored image of the number by using a mode switch. So the mode switch, when it is activated, will cause this to display in a mirrored mode. So let's look down here at the bottom to see an example. This is the number 3, and you'll notice the segments are lit in this way to project the number 3. When the person's looking at it. The mirrored mode would reflect across the vertical line in between here, and so it's a reflection like in a mirror across here. So this becomes the reflection of it. So that's what we're doing. We're just creating a simple FPGA design that takes a value as input, uses a mode switch to determine whether to put it in reflection or normal mode, and then displays it on a single 7-segment display. Basically, I think it will help us to see how this works a little bit by seeing it in action. So what I've done is I've programmed a development board. It really doesn't matter what board you use. I'm using a Digilent Basys3 board. There's tons of them out there that have all kinds of resources on them. So it's nothing special about the board. It's just it has resources that let me do this fairly straightforward. So let's take a look at that board and see how it works. As you can see, the Basys3 board provides all the resources we might need for achieving the goals of this little design. The idea is we're going to have a 7-segment display. We'll use this one here. We're going to have 4 switch inputs, and we can use these 4 switches on the far right as our value input. And then we'll need a mirror mode switch. And so we'll just use the center button in the middle here to do that. So this has all the resources we can use to show this design. But like I said before, it's not the board that's any special. It's basically could be worked on any board that has these resources available to us. What I've done is I've loaded the code into a USB stick right here. And this board does allow us to boot from USB. So when we turn it on our design, we'll get loaded into the system and we'll start working once the load has been loaded in the system. So let's take a look at the normal mode. So not having the button pushed is normal mode. So if we go move these switches up, you'll see that it represents the actual value. So if I put in 1, for instance, I can put in a 5, I can put in dog or D, 1101, there's Fox, let's see, we can put in 3. So it covers all the possible digits or numbers for a 4 bits input. But we also have the mirror mode, which means if I push the button, it'll reflect to the other value. So we started off with 3 in our little example. And so you can see how by pressing the button, it's doing a reflection. Let's pick another number. There's 7. It'll reflect 7 across, just like we showed here. We can reflect 1, which just flips to the other side. Let's see, let's find, there's 2. It goes to looking like 5, but it's a reflection. How about Charlie? There we go, reflect that one. Fox, reflect that one. And so the device is working the way we expect it to, right? We've got the 4 input switches, our mirror mode button, and then our display here showing the actual digit that's on our system. So let's go back to the design and let's look at how the interface and everything comes together. Now, we've seen the board and it's really got the nice resources that show us. Let's take a look at how this design comes together. So this is the overall design, right? But first thing we do when we're setting up a design in VHDL is we have to worry about the interfaces. That's a big deal. So let's take a look at what the interfaces are on our design. You want to spend a lot of time up front making sure your interfaces are specified, because these interfaces can really come back and haunt you later if you haven't done a good job of defining the signals. So make sure at the very least you've defined a really strong interface. Notice here that we have specified quite well the 4-bit input. We've said that this is a 4-bit positive logic input. Now, what does that mean? Well, positive logic refers to logic where a high represents a 1 and a low represents a 0. If it were inverted, that would be called negative logic. You almost never see negative logic out there, but it's important to make that designation and specification. The mode switch, we tell you exactly what a high means. It means you're in mirrored mode. So by default, if it's not high and it's a low, that means you're in normal mode. And here, the 7-segment display basically shows you that you have an active low, and that means a low means the LED is on. So this is not unusual in some LEDs because of the way they're made to have a low activate the LED in a 7-segment display. So it's a little different than we're used to maybe with an LED, which you light with a high, but it all depends electrically on how it's connected to the port pin. And that can vary depending on a variety of reasons. So one thing I want to pay attention to before we move on is how the 7-segment displays are numbered, because that's a big deal. So if we take a look at the numbering scheme that's shown here, you'll notice that each LED inside the 7-segment has a designated letter. And this is standard across the industry as far as LED numbering. We have the letter A for the top, and it just circles around to the other side and then goes to G. So we start with A, so it makes it easy to remember. You start with A at the top, and you go A, B, C, D, E, F, and then the inner one is G. And so that helps you refer to the segments in a way that makes it easier for you to design your interface. So this is also part of the interface, is understanding how the displays are numbered and how everything is formed. And we're going to have to decide in our vector that represents this what the ordering is. Okay? So to do that, we go from our specification to create an entity, which is basically the box. Remember, an entity is the box with inputs and outputs labeled. And so we're going to call our entity mirrored segs or segments. That's going to be the name of our entity. And then what we're going to end up doing is specifying each input. Now for value, we're going to make that a standard logic vector 3 down to 0, so it's a 4-bit value. This is a standard way of specifying a 4-bit input. And we're going to assume that this is basically a standard numeric value with the most significant bit is bit 3 and the least significant bit 0. That's pretty much standard across the industry if it's not specified. The next thing is the mode, and the mode is just a standard logic input. And then the next one would be our 7seg, which is an output, and it is a 7-bit output. Each bit represents one of those segments. And this basically tells us the ordering of those segments from left to right is A, B, C, D, E, F, G. Remember, we numbered them or lettered them A, B, C, D, E, F, G all around. That's standard in the industry. And so I'm telling you here in the vector, this is the order of the bits in the vector, okay? So this design is making this assumption about the order of the bits. Now, one of the interesting things about the Basys3 board is they order the bits differently. And we're gonna see how we fix that when we use our component, our design in another external component. And we'll be talking about a concept I call my chip. And we'll get to that at the end. So when we're setting about designing this, remember, the entity describes the whole box with the inputs and outputs. We understand what the signals are. We know that some are vectors and some are just standard logic. We've clearly specified what a high and a low means on each of those inputs. So now we're ready to dive into the inner workings, right? And so when we're designing the inner workings of our system, we have to find a way to approach it. Now, what we've learned so far is combinational logic stuff, and we can solve this problem all with combinational logic, which is nice. So we have to think in terms, though, of how we're going to do that. Obviously, there are a lot of different combinational logic functions out there, so you have to kind of brainstorm what's happening. So if we think about it a little bit, you'll notice that, well, we have a value input, right? And the value input needs to be somehow translated into normal segments, right? And it was going to have to be transmitted into mirrored segments because they're different. The way the display looks is different, so we have to change the segments to meet that. So we could somehow have a decoder that might create the normal segments, and then we could have a decoder that would create the mirrored segments. Now, when you're going through this process, it's okay to just start jotting down ideas. Just because you write it down on paper doesn't necessarily mean it's going to be the way you approach it in the end. A lot of times the practice of brainstorming and trying to figure out a design is partly doing this, just writing things out, kind of playing with the diagrams, moving things around, and then finally finding something that clicks or fits into the design. This is why VHDL designers are paid the big bucks, is because they have to really do a lot of thinking about how to organize this. Now, as we get further along in our course, there are decisions you have to make as to how to approach the problem to create the most optimal hardware usage, right? And so there's lots of little techniques I'll teach you later on how to do that. But for now, let's just look at the overall design and see what's happening. Now, obviously, the mode switch is going to come in here somewhere. And the mode switch has to come in and make some decisions. Now, one of the elements that we've talked about for combinational logic was basically the decoder or a code converter, or however you want to call it. So it could be just a code converter. We're taking a coded binary value and outputting a 7-segment. So let's just call this a code converter. And this is also a code converter. And so we're going to run this, but what we need to do is we need to select one or the other, right? So the idea is I'm going to select either the normal segments or the mirrored segments, and it all depends on the mode input, right? So what's a great combinational logic device for selecting things? Well, a multiplexer is perfect for that. So if we put a multiplexer here, and then this could go out to the 7 segments on our display, and the mode could be used to switch between the 2 possible segments. Now I know this is a 7-bit bus and this is a 7-bit bus, but that's fine. Multiplexers can switch multiple signals and you treat them as one big signal. Remember, it's a standard logic vector, so we can treat it as a single entity inside VHDL. And it will handle the routing of the different ones. Remember, this is also a 4-bit input, so we would kind of draw it that way. So we're looking at the problem, trying to figure out ideas. This is a relatively simple problem, so it didn't take a lot of effort. Sometimes you might spend days trying to map out design. Say if you're creating a new communication protocol and you're looking at how to sample the waveform to make sure you preserve the details of the wave in your representation. So all of that stuff is going to be figured in, and you have to spend time designing that. The brunt of the work in VHDL, the real meat of it, is doing this. It's the design part, not the writing code. Anybody can write the code, really. It's the planning out the design that's the complexity. It's the figuring out what's the most optimal solution, which will provide you the highest speed for your clocking frequency, the lowest, power consumption potentially, depending on what it is you're doing and what device you're targeting. So there's a lot that goes on in the design process. Well, let's take this and let's formalize this into a nice diagram. And let's talk about how the boxes are represented. So if we look at the design, you'll see that I'm representing the port inputs with these little port connectors here that show that this is an input of value. This is a mode input, and then here is the 7-seg output for our design. Now, we decided on these when we created our entity. So our entity really determined the naming and the size. This is 4 bits, and that's 7 bits for these interfaces. Now, we're trying to create the meat or the internal part of it. And so to do that, what we've done is we've created our code converters. There's our mirror segs code converter, and this is our normal segs code converter. So a lot of times when you create a combinational logic block that actually drives a signal, and it is the source of that signal, you will name the box itself using the all caps notation with the same name as the signal. Now notice the signal is lower camel case, but the name of the box is all uppercase, the same name. That helps correlate the box in the diagram with the actual signal that it's driving. Makes it a little easier to read. And then, of course, we have our multiplexer here, driven by the mode input that decides which one of these segments that I want to select. So that's it. So we've created a really neat design that basically will convert a 4-bit value on the input into a 7-segment representation on the output, and it will be mirrored or normal based upon the mode input that's fed in there. So that's kind of the inner workings of our overall design. To get started, one of the things that's going to really help us is before we define these boxes, before we define the mirror segs box, the normal seg box, and the multiplexer functionality inside our code, we still need to define the signals that are all part of this, right? So we're going to have to define a mirrored seg internal signal and an internal signal called normal segs as well. So these are going to have to be defined. But the other thing that we're going to have to think about is the values assigned here. So this is a 7-bit value that's designed to drive a particular interface, a particular 7-segment display. And remember, it's active low on the display. So let's take a look at this. What I've done is in the code, I've created a set of constants that actually represent the 7 segments. Okay, so I've created a set of constants that basically represent each state. So this is a blank state. So we wanted a blank state so that the 7 segments could be just blank. And that means all bits are 1. That makes sense. A 1 turns off the LED, a 0 turns the LED on. Let's pick up another one that could be interesting to see. How about a 7? Let's do a 7 and see what that bit pattern is. Now the bit pattern is 0, 0, 0, 1, 1, 1, 1. So if we redraw our 7 segment display out here to the side, and then you can see how this number came about, right? So here's our display. This is the A, B, C, D, E, and F, and the middle one here is G. So if we're wanting to display a 7, we need this one to be on. So we're gonna turn this one on, and this one on, and that one on. So that's gonna make us a 7, right? So what did we say with this particular interface? A 0 turns them on, a 1 turns them off. So if A is the leftmost bit in our number, it's going to be 0, 0, 0, right? Because 0, 0, 0 turns those on. And then the rest of them are off. 1, 1, 1, and then 1. So it'd be 1, 1, 1, and 1. So that number, that vector, will be used to make the number 7 on our display. And so if you look down here, that's exactly what we have here, 0, 0, 0, 1, 1, 1, 1. You can do this for every single number we have and see how the 0 corresponds to the segment being on and the 1 corresponds to the segment being off. Now, if I tried to hard code this in my code, it would be a nightmare. And what if I made a mistake? Because mistakes do happen. What if I had accidentally made this 0, 0, 1, 0, 1, 1, 1, and it was an accident, it was a mistake, and I put that under in my code, then everywhere a 7 was supposed to appear, I would see whatever this creates, and then I would go, my goodness, now I've got to go through my code and change every occurrence of that. But if I create a constant, and we've talked about this before, how important they are. If I create a constant and I call it, 7 for the 7 segments, so it's the number 7 represented in the 7 segment display, and I figured out I did it wrong, I just go back and change it here. And once I've changed it here, it changes it everywhere it's used in the code. So you never hard code these numbers in your code. Well, there are some exceptions, which we'll talk about in a second, but normally you never do that. You would always put them in constants. So this is the normal segs, right? So we would do that, and then we would declare constants for the mirrored segs as well, right? So we're going to do the same idea for the mirrored segs. We're going to give them a different name. In this case, this would be constant 7 seg mirror, and we use different values because the 7 segs are going to be different for a flipped 7 as opposed to the regular 7. And so you can go through and look at each one of these and see that. Now, in addition to this, to clean things up and make it more readable, we've created the mirror segs and we've created the normal segment constants. We should also create a constant to represent our mode as well. And so we can create a special constant called mirrored mode and say that mirrored mode is represented by a high. And that's what we agreed upon when we talked about our interface. When the mode switch has a high on the input, that means it's mirrored mode. So we can basically solidify that in our design by declaring it as a constant in our program. The next thing is those interconnecting signals. And so here what we can do is we declare the normal segs and the mirror segs as a signal inside our design. And they're both standard logic 6 down to 0 because they hold the 7-bit value for the mirrored segs and for the normal segs, right? So that makes a lot of sense in this case. And then it's time to start defining the functionality. So we've defined the constants that represent the values that are part of our system. We've defined the signals that are interconnecting the boxes in our system. We can see that from our block diagram. And now it's time to declare the functionality of the system and basically how the function works in our system. So let's start with the mirrored segs. And we're going to be implementing the mirrored segs with a fairly simple selected signal assignment statement. By using the value as the input, we can specify all the values for a 4-bit value, all 16, and then tell which one of the hard-coded constants are going to be assigned to the mirrored segs for which input value. So every time a different value happens on the input, it will pick a different representation of the 7 segments. And that's a pretty straightforward operation. Now remember when we said we don't hard code values in VHDL? There are exceptions, and this is one of them. And that is if you're listing things in order. So let's go back, let's get rid of that. If we're listing things in order, like here, then if it's in a numerical order, a counting order, then go ahead and list them out. Everybody understands that. You're not losing information. There's nothing special here. It starts with 0, 1, 2, 3, 4, 5, 6, all the way down. And then notice the others. We talked about the others clause before and how important that is to make sure this is combinational logic. Remember, we don't want any storage in here. There's no flip-flops. So we want to make sure that that happens by putting the others. But this is fine not specifying constants for because it's just a numerical sequence. The other exception to the rule is if you're initializing something to 0, for instance. That's fine as well. You don't need a constant for that. All right, so that's mirrored segs, where it takes the value input and outputs a mirrored segs. Let's take a look at the normal segs, where it takes a value and puts out the normal segs. And as you probably can recognize now, it's just the same thing. So basically we have a value as the input. We're using all the possible values to define what normal segs is going to have. And this is the representation, the 7-bit representation for each of those displays. And then finally, we have our multiplexer. And again, another selected signal assignment statement. So the thing here is selected signal assignment statements are incredibly powerful and often used for combinational logic. They provide some of the easiest ways to describe common combinational logic functionality, and it's very easy for the synthesis tool to synthesize a design using that. So it really simplifies things from that point of view too. So here we go. We come in with the mode. That's our selector right here. And basically, when the mode is mirrored mode, see how that reads? If I had put 1, it wouldn't have been as clear. And if I wanted to change my active mirror mode, I could change it in the constants. But, you know, this reads like a book. You just come in and say, all right, with the mode, I'm going to assign mirrored segs to the 7-segment display. Ooh, that's wrong. That should be 7 segs. So I need to fix that. So that should be 7 seg, like that, because that corresponds to this signal over here. So these are the same. And then basically, if it's in mirrored mode, then mirrored segs get assigned. Otherwise, normal segs get assigned in other cases. So again, we're creating combinational logic. There's no storage here. We're not trying to store a value. We're just responding to changing input values on the value when the value comes in. And then what outputs on the multiplexer depends on the mode that's coming in, okay? So this is pretty much the way in which you define this. Now, the next step of the operation is, okay, so now we've defined it. What does it all look like in code? So let's take a look at the code and see how that comes together. Okay, so now that we've seen all the individual pieces that make up the mirrored segs design, let's see it come together in the full file. And this file, we show all the aspects of a good VHDL file, a well-commented header. So up here at the top, we see a nice well-commented header that tells you not only the name of the component, but also who designed it, as well as a full description of what's going on inside. This is the first place a designer will go to find out more about your component. We'll see the entity description that, you know, for our segment, mirrored segment, showing the value input, the mode input, and the 7 seg input. So this is the component we just created for driving the mirrored segs. The architecture for this component is defined here, and you see all the constants that we talked about before and how the constants are set up so that they're right here at the top of the file in the declaration area. So we have our mirror mode constant. These are the constants for this normal 7 segments, and this is the constants for the mirrored 7 segments. Then we also get down to our internal signals, all pieced together nicely. And then we also come down and see the actual code itself. So notice that the individual blocks have been commented so that you can easily find them in the code itself. And then there's your selected signal assignment statements for each aspect of the overall design. So that's the full file together, and that should create a nice component for us to use in our system. Now the next step we're going to want to do is we're going to want to take this design and we're going to put it in hardware, which means we have to somehow map all of these input-output signals to actual hardware. Now I could have done that in this file by using a configuration file supplied by whoever the board manufacturer, whoever I'm using, and then use their naming scheme and put that here. But I think sometimes that's not the best solution. You really need to design your components to be independent of any hardware, any board design. And so to do that, you would isolate your component, give it the names that it needs, and then you would embed your component in an external component that's simply designed to do the interfacing for you. So I tend to call that my chip so that it emphasizes the fact that this is an actual FPGA chip that you're interfacing to. And then inside my chip, we'll put our design. So if we look at that, it looks a little bit like the following. So if we go with that idea and we start looking at the actual hardware where we're going to create the my chip component, it's going to look a lot like this. We're going to basically drop in our component, which is the segment driver component we were just looking at the code for, and notice it has the value input, it has the mode input and the 7seg output, but we're also attaching it to an external signal here for doing some really strange things. It looks strange at first, but I'll explain what's going on here. So in our particular board, so this is targeting the Basys3 board from Digilent. I mean, like I said, the board's irrelevant. All that matters is that your design interfaces properly to the switches and LEDs and other resources that you're wanting to. And so all of these resources are tied to specific pins on whatever board you're targeting, and you have to map those pins to the actual ports that are in your design. Now to do that, there's a configuration file. Now in our very first VHDL project, we went through the whole process of opening a configuration file and uncommenting the areas that we're going to use, such as switches and LEDs. So you'll want to do the same thing here, is you'll need to uncomment the configuration file and make that a part of the overall design. So you're going to make the switches, the lower 4 switches, part of your configuration. You're going to make the button, the center button, part of your configuration, and then you're going to also make the segs part of your configuration. Now once you've done that, you'll be creating this mychip.vhd file, which is a new component, and embedding inside of it the component we created in the other file, this segment driver component. Now, because of the way the Basys board is made, it is different than the way we developed our segment code. So in our segment code, we made the decision to start on the left with A, segment A, and then all the way to G is the far right bit. Well, Basys did it the opposite. So they made segment A bit 0, and then they made the segment G bit 6. So what we can easily fix this in this outer component. That's the nice thing about having an encapsulating my chip component, is it allows you to interface to external devices that may be changed. Like for instance, let's say you wanted to use this driver component in somebody else's board, right? If you had written the component with their names, then you would be limited. You could have to use their names for your rest of your design. But since you use the My Chip idea, then you're going to be able to drop your component in anybody's board and attach it to whatever resources they have and make it useful. So you're independent, vendor independent. You're not dependent on any one board or any one company for your design. And that's always a good thing to do. You do not want to ever tie yourself down unless you have to because of various resources that might be provided by that particular company. But normally that's just not the case. Normally that's not something you need to even worry about. So right here we see, and this is the only confusing part I want to spend a little time explaining, is we've created an internal signal called 7seg. Now remember, this 7seg is the port in our component, okay? It's the port in our component. It's not visible inside my chip. It is part of the component. So we have to attach that port to an external signal. And that's what this is. This is the external signal. I use the same name just to make sure that it reduces confusion as to how the interface goes, right? I didn't have to. I could have called it Bob if I wanted to, but it makes more sense to call it the same name. But this is the signal inside the design. This is the port of the component I'm putting in the design. And when I instantiate my component, I will be making this connection obvious when I create it in my VHDL code. And we'll see that in a second. So the big thing here is we're swapping bits, and there's a lot of different ways to do this. You can do this in a process, which we'll see later. We can do stuff with for loops and stuff, but something so simple as these 6 lines makes very little sense to do anything super complicated and run the risk of having an error. You've only got 6 lines, so just write it out. Put 6 lines in there in your VHDL code and make it so. So basically, we have this bits from our 7-segment signal being attached to these bits of our segment signal that goes to the basis board. And you'll notice that bit 6 of the internal design connects to the basis board's bit 0 for their segments. Bit 5 connects to 1 and all the way down until bit 0 connects to bit 6 on the segment component. So we basically inverted or swapped the bits around, and we can easily do that in VHDL using our concatenation operation. So let's look at what this would look like in code. So now we're going to take a look at the MyChip code, the actual code that creates that thing that holds our design in it, and we attach to the pins of the basis board. So notice that it looks just like any other VHDL file with the NT architecture. I've given the name MyChip to emphasize the fact that we're really getting close to the hardware now, and we're tying to those hardware pins. The hardware pins specifically, the basis configuration file references their slide switches as SWs, or you use that notation. They reference their center button for their digital button pad as button C. That's going to be great. The segments are also referenced here, but also the anodes. Now, because of the nature of the basis board, there's 4 digits inside their 7-segment display, and they share the same segments with all those digits. And the way you control which digit is displayed is by activating the proper anode. The anodes are all active low, as well as the segments are active low in the design. And we talked about that earlier, but that's the way it's configured. So in order to turn on the LED the 7-segment display that we used in the board example at the beginning, we have to activate the rightmost LED. And to do that, we create a custom constant here called select right 7-segment display. Now notice how that constant is a very large name, but it's also incredibly meaningful. And it means that when I start my code and I have a line like this, it's pretty easy to see what it's doing. Basically, I'm assigning to the anode a select right 7-segment display. There's no mystery there. That's exactly what's going on. And you want your comments, your variable names, or your constants and your variable names to have meaning, to make your code just readable just by looking at the variable name. And this is a good example of that. We also talked about how we had to switch around the signals for the segments, And this is that section of code that basically just swaps out the bits, the lower bits. It just inverts all the bits, and it does it one bit at a time. And since it's a bus, we can activate the individual bits simply by using a single parentheses and a single number in a parentheses after the name of the vector. And that gives us access to that single bit. And that's excellent too. We also have to instantiate or put our component in the system. And this is where we create our segment driver and we attach it to the various signals. So the diagram showed us attaching the switches to the value input. So notice that we're using named association here. And so value goes to switch, mode goes to button C. So button C is going to be used to change the mode. And then of course the 7seg goes to 7seg because we created that internal signal so that it would allow us to flip and swap the bits and it would work with this hardware. By doing this my chip idea, we're able to attach to any external hardware we want to, irregardless of how they wired up their segments and anodes. So that keeps the flexibility up when we make our designs that way. So that's the end of our full design. So we went from the beginning to the end of a nice little complex combinational design. Hopefully we were able to see various aspects of design that might help you get further in your understanding of VHDL. And we're about to dive into some really complex stuff. We're going to start talking about processes and also delta cycles and other things. So stay tuned. We'll see you guys in the next video. Thanks.